Welcome to the lecture on cold weather concerns during construction from a design perspective. The learning objectives for this module are to first understand the weather and temperature how the weather and temperature specifically will affect the design and construction process. Two, to apply the principles of concrete design to predict the effects of cold weather. And three, analyze solutions for dealing with cold weather on site. So the first topic I'm going to discuss is frost heave. Frost heave is the upward movement of soil from ice formation and expansion underneath. We are all familiar with the concept that freezing water expands, and this is no different. Think that freezing soil near the surface will expand upward into the looser soil rather than downward into more compacted soil layers. In the component design module, we discussed minimum embedment depths in the context of scour and soil bearing capacity. A stipulation in the IBC Chapter 18, Section 1809.5 also mentions that minimum embedment depth should be underneath the frost line in order to protect from frost heave. And I've drawn a little graphic here to kind of explain as you get deeper underground, the temperature is more stable. It's closer to 55 degrees, and we're less likely to see frost or freezing happen as we go lower and lower. So the frost line and the distance to the frost line is going to depend on properties of the soil. It's going to depend on the climate and how many freezing days we have in a row. So how we actually find the frost line is going to be beyond our scope for finding the exact frost line because we don't have that granularity of soil data. But here we'll go through a short thought experiment using an empirical model that doesn't require too much information about the soil properties to kind of give us an idea of what a normal value of frost line would be. Another thing you can do is you can look up maps of frost depth across the US and other places that information has been mapped out. So we'll start with three equations. P is going to be equal to negative 0.45 K plus 1.9614 times our CFI to the power of 0.0913 K plus 0.4143. So this is obviously an empirically derived and fitted equation for this variables K, which is going to be the thermal conductivity of our soil, and CFI. The daily freezing index is summed each day to find the CFI, and that's I've abbreviated as DFI, which is going to be 32 degrees Fahrenheit or freezing minus the Tmax plus Tmin of the day divided by 2. And every time that is greater than or equal to 0, we're going to count 1 for our CFI. So the CFI is basically just a measure of how many days the average temperature was below freezing, written in equation form. And this is our input into the equation P in combination with thermal conductivity to find our frost line depth. And our value P is going to be that distance to the frost line from the surface. Now, we can still use the equation to predict frost line, making some assumptions, and tweak our values to rule out the possibility of frost heaves significantly affecting our abutments. The example we'll take is for the Bolivian Altiplano, which is a highest elevation and coldest area that we currently work in. We can take K for a clay soil, which is going to be a pretty conservative estimate as 1.01 BTU per feet hour degrees Fahrenheit. And if we plug that in along with a CFI of, let's say, 100, which is highly unrealistic, we're likely going to have much less than 100 days in which the average temperature is greater than freezing. But let's just say we plug in the value of 100 with a pretty conservative thermal conductivity value. We get a value of P of around 39 centimeters. So this tells us that even in kind of a, wild case that's likely never going to happen, we still only have a 39 centimeter P. So if our foundation is embedded 1 meter into the ground, we are sufficiently below the frost line and don't have to worry about frost heave. Now, if you're at a really cold site and this is a concern, and say you're planning to have your anchor or your ramp walls embedded only 30 centimeters into the ground, this may be something to consider in your design process.